Welcome to solverfy.
.48, we're considering the alpha decay of uranium-238. We want to figure out how much the energy changes or is released when it emits an alpha particle, and then when it releases a neutron, a proton, a neutron, and a proton. We want to argue that the difference of this is the binding energy of an alpha particle, and also then find what that is. And then we're given a table of things we need. So here, this decay is uranium-238 goes to thorium-234 plus a helium. So the energy that this releases is just the difference in the mass of the uranium and the mass of the products times c squared. And so this is 4.25 mega electron volts. So for part B here, we have our uranium, which we pull out a neutron, so that turns into uranium-237 plus a neutron. Then we have our uranium-237, and we take out a proton. And so this becomes protactinium-236. I think Pa is protactinium. Plus a proton. Now our protactinium-236 decays into, we take out a neutron, so it decays into protactinium-235 plus a neutron. And then our protactinium-235 decays into a proton plus thorium-234. And you'll note that we're given the masses for all of these. Be continued. To keep track of things, let's call the first one delta E1 and the second one delta E2. And so this is an annoying long expression, but we have to do it. So we have the difference in mass in uranium-238 and its products. 237 uranium minus the mass of a neutron. we add to that the next decay, and the difference in masses, rather, of that decay. So the mass of the uranium-237 minus the mass of the protactinium-236 and the mass of the proton. Then our next step, mass of protactinium-236 minus the masses of the 235 and the neutron we just removed in this step, plus the next decay, which is protactinium-235 minus the thorium and the proton. And mercifully, for the purposes of actually numerically evaluating this simplifies quite a bit. Because, for example, we have minus 237 uranium here, plus uranium-237 here. That should be an N. Minus and plus protactinium-236 and 235. So what we end up with is the difference between the mass of the uranium we start with, the two neutrons we remove, two protons we remove, and the thorium that we're left with times c squared. Now this comes out to negative 24.1 mega electron volts. So this it would make sense for the difference between this and the one we just found in part A, with just taking the alpha particle out in its entirety all at once, because here we're basically disassembling the alpha particle in the process of removing it. And so the energy that is required to disassemble some nucleon, or not nucleon, a nucleus is the binding energy. So we have, for the binding energy is going to be 2 times the mass of the proton plus 2 times the mass of the neutron minus the mass of a helium. We just care about the absolute values here, times c squared. That's going to be equal to the difference in absolute value, just so we don't have to keep track of the signs, between these, 4.25 that's in mega electron volts. So we conclude that the binding energy of the alpha particle, both from directly calculating it and taking the difference of these things, is 28.3 mega electron volts.